All right, so we left off talking about mass spec. We talked about the different we looked at 5 different molecules and we used the spectrum and the molecular weight to match up a compound with that particular spectrum. So and one of the things we talked about was how molecules break apart, how cleavage happens. And so I'm going to talk about that for a minute today, and then I'm going to talk about an example where mass spec could be used in practice, and then we're going to work through the examples at the end of that NMR handout. So hopefully you printed it or you have access to it, because we're going to work through those examples today. Then on Monday, we're going to start infrared. We'll start infrared, which is a fairly, none of this stuff is simple, but it's a fairly easy topic to understand. It's none of it is simple. I just try to make it simple as possible so that we can understand it and grasp it. But the technology behind it is all very, very much complicated. All right, so let's look at some cleavage patterns for mass spec. And there are a bunch of them, but they're fairly, how do I put it? They're fairly easy to recognize, right? So if you have a branched alkane, like as in example 1, right? Cleavage is favored at those branch points. You can see right here, this part is branched. And when you cleave that off, remember the radical cation, the positive charge is going to go with one fragment and the radical is going with the other fragment. So over here, you can see at that cleavage point, if I cleaved here, where I have the line drawn, right, that's breaking that carbon-carbon bond. And so over here, these are your 2 fragments. Notice I put the plus charge on the secondary carbon. And then the radical is here on the primary carbon. Not as stable, but a primary radical is more stable than a primary carbocation. So that's how we have to look at that, because these fragments, again, the identity of the fragment is going to be based on how stable it is, right? So what the one that becomes the cation is going to be most stable as a cation. The one that becomes a radical is going to be most stable as a radical. If you have a double bond, an alkene, the cleavage that occurs there is at the allylic site. Remember, this is the allylic site right here. Right, the site that's right next door to the alkene, that carbon is allylic. And so that's where the cleavage happens. So here, between these 2 carbons, I'm breaking that bond. Right, so I'll get an allylic cation. You've seen this before. It's resonance stabilized, and I get a methyl radical, right? Because again, let me write it out here. This is a radical cation. And so one of those species is going to become the cation. The other one is going to become the radical. So I get a methyl radical and the allylic cation. So if I have a double bond present, it's not going to chop the pi bond in half. It's not going to chop the double bond in half. It's going to cleave at an allylic location, because again, even though in theory you could break that molecule up into whatever pieces you want to, practically it's about stability, the stability of the fragment. So there's another cleavage pattern called alpha cleavage, right? And that's that's bonds that are adjacent to a heteroatom. We saw that when we were looking at our example on Wednesday, right? So if you look here, I have an alcohol, and the adjacent carbons to that alcohol would be here and here, right? So that's where that's going to break. It's going to break here and here, because those carbons, just like when we study E2 elimination, and we talked about alpha protons that are adjacent to where your leaving group is. This is not, I'm not saying that OH is a leaving group. What I'm saying is the position next to that functional group, those positions are considered alpha. We call them alpha carbons. So that's why we call this alpha cleavage, right? So if I break that alcohol, if I chop it, and these are blank on purpose. So somebody help me out with, let's say I did this side first, what 2 fragments would I get? If I cleaved at that position first, what would I get?
Get, what do you call an alkyl with an N to have CH2 plus?
So here,
Mhm.
right, you're saying that this carbon right here, right? You said that's a CH2. And then I'm also
Yes,
going to
yeah.
get, what else would I get? Because I'm breaking that bond, and that's very important to understand. This bond right here is going to be broken between those 2 carbons. That bond no longer exists, so I'm going to get those 2 fragments.
Yeah, so it's like a carbon attached to the OH in the other alkyl.
You saying like that?
I don't know about. Yes, I don't know about any charging. It's the charge.
So yeah, you're right. And I have a choice. I can put the plus charge on either one and make either one the radical. But I'm gonna put the plus charge here on this carbon because oxygen, it has lone pairs and it can actually stabilize that plus charge by resonance by making a pi bond here. Right? So this is resonance stabilized. Right? And then I'll put the radical here. Like that. Good. All right. And then obviously if I cleave the other side, I'm going to get 2 different fragments. I'm going to get a fragment that looks like this, which will be a CH2, CH3. I'll get that. I'm going to make that the radical. And then plus this. And again, I'm going to make that the cation. Right. So that's how we approach a problem like this. If you're asked to give the fragments from a particular cleavage pattern, then that's how you attack it. You find, if it's alpha cleavage, you find the functional group, whether it's an alcohol or an amine or a carbonyl, and you break the carbon-carbon bond on the adjacent carbon. Let's do the next one. Somebody help me with the next one. Go ahead.
For the second part, why does it have an extra carbon bond? Right?
You said an extra. Let me count. Let's see.
Like the
1, 2, 3, 4 carbons. 1, 2, 3. That's four carbons. Are you talking about here?
No, on the right. I thought it had like more groups.
It's 4 carbons. Right. This is this piece right here. Right. So that's a carbon, that's a carbon, that's a carbon, and that's a carbon. So that's what I have over here, right? 1, 2, 3, 4 carbons.
Okay, sorry.
That's okay. Right. The next example is going to do the same thing. Can somebody annotate that? If you're able to annotate and write in the 2 fragments from that.
Well, I mean, no. I mean, my handwriting is. I struggle. I can try.
Go ahead.
Just put it in. That's supposed to say CH2. Right.
What side are you doing?
The
left side. Okay.
and then that's supposed to be. Oh Lord. It's supposed to say NH2.
I got you.
And then I can. It's supposed to be.
Okay. I can interpret that. And,
Okay.
and it's correct. Where would you put the plus charge? I'm gonna write it out too, but I do see, I get the gist of what you just put
Great.
on the screen.
Make sure you erase that.
Yeah, yeah.
Okay.
We're gonna clear it up.
Put the plus charge. I guess just like the last one, we put it on the.
We put it adjacent to nitrogen, right? Because again, nitrogen has long pairs and they can do resonance. So it can stabilize that plus charge. And then on the other carbon, that's where you would put your radical. Right. So let me clear that. And then I'll rewrite it because you already wrote it. All right. So we're doing this side first. All right. So you're going to get a similar pattern. It's really the same thing, just a different functional group. Plus charge here and a radical there. And again, with nitrogen having that long pair, it can do resonance and stabilize that cation. So that's why I want to put that right there. All right. Any questions about that example? All right. And obviously I'm gonna let you do this one yourself. Obviously, and I want you to do both sides and finish this side also. Right. But obviously you can see that the alpha cleavage happens again adjacent to your functional groups. And there's one other cleavage pattern is dehydration. Most of the times you see this with alcohols. So you got an alcohol here, and you are with that dehydration, what you're going to do is you'll lose water because it's an elimination, right? So one of these protons right here, well, no, the other side, sorry. One of these protons here. Gets removed in the process, and you end up with water and an alkene. So this is a dehydration. All right. Where would you see water in the spectrum? Let's just say if you had this alcohol right here, where would water show up in the spectrum? What do we need to know in order to answer that question? And what are we looking at with respect to mass spec? If we're studying mass spec, what is the basis of our study? What are we studying? What does mass spec tell us?
Atomic weight.
Yeah, so molecular weight, molar mass, right? So if I have water in my spectrum, where should that show up?
Wait, you said if it's dehydrated, what would happen?
So if I get water, if the cleavage pattern is dehydration on this alcohol, where will water show up on the spectrum?
Would it? I don't think it would.
It would. What's the
Oh.
Okay, so let me ask it a different way. What's the molecular weight of water?
It's like 30.
So oxygen is 16, hydrogen is 1.
Yeah.
So it's
But there's
18
two hydrogen. It's just like
grams per mole. So in a spectrum, let's say we took the spectrum of this alcohol, it would be water is at 18 grams per mole, and then we have 1, 2, 3, 4, 5 carbons, that's 60. and then 3, 6, 8, 9, 10 hydrogen, so 70. So this thing is 88 grams per mole, and then the alkene is 70 grams per mole, and then the water would be 18. All right. Any questions about the cleavage patterns? So you have dehydration, alpha cleavage, allylic cleavage, and then branched cleavage. All right, and I'll make sure that you are able to I'll post a blank PowerPoint so you can grab this part right here if you want to practice or you want to, or you need to finish the other two anyway, so you need a blank. So I'll post the PowerPoint itself to Blackboard when I post the notes today. All right. Any questions about anything? Right. So here's another example. In the PowerPoint I didn't have the pieces down here shown. I actually had I faded them in so to give you a chance to think about it. But if you have a reaction like this, which is what's that reaction up top? Anybody? We took an exam on it, so you should be able to tell me. NBS and light in the presence of an alkene.
Oh God. Allylic bromination.
Yes, it's allylic bromination. Good. So if you did that, right, this is one way mass spec is used, right? So the molecular weight of your starting material is 112. If I add in a bromine, right, the molecular weight goes up to 190. And if I say I have this allylic bromide, I need to prove it. So if I did a mass spectrum on that, I should see what would the parent peak be if I did a mass spec on this compound. Where would the parent peak show up? In the spectrum. And what is the parent peak? Help me out. We got 12 people in the room, or 11 people, include myself, that makes 12. So where is the parent peak and what does it represent?
The parent peak is going to be at 190.
It's 190. It's the molecular weight of the compound. What would be the M plus 1 peak? M plus 1. If the parent is 190, then the mass plus 1 will be what?
The base.
It would be 191, right? Not the base peak. I'm talking about the isotope peak. Remember, you have the parent, which in this case is going to be 190 grams per mole. And then you'll have your M plus 1, which will be 191 grams per mole. Remember, that's the isotope peak. And then if these are the fragments that this gets cleaved into, right? The base peak is probably going to be between 148 and 111. It's going to be one of those two, whichever one is the more stable cation, right? It's either going to be 148 or 111. Right? Because the base peak is the most intense peak in the spectrum, and it's also it also corresponds to the most stable fragment. So it's going to be one of those two. But we wouldn't be able to tell that unless we actually did the mass spec on this compound. All right, any questions about that? All right, let's look
No,
at it.
sir.
Go ahead.
No, I was just saying no. I mean,
Okay.
well, actually, I had a question, but it's not really related. It's related. So the back of the NMR,
Mm-hmm.
I see the part where it's part two mass spec,
Mm-hmm.
but the problems you were just doing, is that a separate thing, or are we just doing this for practice?
We're gonna the one you mean what are we gonna so the other part is separate, right? Just that's for practice. What we're gonna do at the end of that handout, that's to be turned in with the exam,
Okay.
along with the
Okay.
homework from the well, I don't want to say homework, but along from the work from the previous section, which I think is what did we do before this? Aromatics
Bef-
and cycloaddition. Those are the three topics on the exam: aromatics, cycloaddition, and mass spec.
Okay.
All right, so let's look at this example. It says a patient mysteriously dies. It is believed that the patient has been poisoned by his wife. Crime scene investigators suspect that the patient has been exposed to dioxin, which is the second deadliest poison on Earth, with a lethal dose of 5 milligrams per kilogram of body weight. How will they find out? What's does anybody know what the deadliest poison on the planet is?
Cyanide?
It's not cyanide. That's pretty deadly though. And it suffocates you because it replaces it's linear, has a linear geometry like oxygen. So if you breathe it in, or if you ingest it, or if it's injected, which is most of the time how it's done in the movies, they have a little syringe full of cyanide, but it actually replaces the oxygen in your hemoglobin. That's how it kills you. So it basically suffocates you without actually suffocating you. But it's not cyanide. It's something that you'll never suspect. Botox.
Carbon monoxide. Oh,
Botox. Carbon monoxide is not really a poison unless it's inhaled in large amounts. Like there's carbon monoxide in every room or whatever, wherever we go, but the concentration is so low that it doesn't pose a threat. It's only a threat when it's highly concentrated. But it's Botox, believe it or not. So when people get Botox injections, that Botox is very, 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 very dilute. Number one, I mean, very dilute, like micrograms dilute. And what they see as swelling or what they see as filling is actually an inflammatory response to Botox from the body. That's why wrinkles fill in and things like that, because it's that tissue is swelling because it's a reaction from the body to fight off the poison. So if you were considering doing Botox, reconsider it because it's really like the deadliest poison on the planet. Anyway, that's an aside. How are we gonna find out if this woman killed her husband? What can we test if we think he's been poisoned? What can we test to find that out? What's the most basic test we can do? I mean, you can test the
You like a blood
organ.
test?
You can do a blood test, right? Blood is a liquid, and if you wanted to test for dioxin, and you knew what dioxin looked like, which is right here, right? You knew the structure and the molecular weight. If you did a blood test, you could find out if there were traces of dioxin in that person's system because it has a molecular weight of 324 grams per mole. That will be the parent peak that we'll look for in the mass spec for dioxin. But with blood, there's so many other different types of chemicals. That other stuff is going to show up as well. But I'm looking for this at 324. This won't be the only thing I do to convict this person, but it'll be one test out of many to find out if this person had been poisoned by dioxin. So this is a class of chemicals, right? It's 210 chemicals in the family. The one that's on the screen is the most toxic out of all of them. And it's a carcinogen It is causes liver damage, genetic defects. It's the same compound that was used in Agent Orange in the Vietnam War. I don't know how many of you have ever heard of Agent Orange, but it was a chemical weapon that was used against the Vietnamese. But the soldiers also got exposed to it who were using it, who were applying it, and many of them still suffer the effects of being exposed to Agent Orange today. I got a cousin right now. He's had leukemia for 19 years, being exposed to Agent Orange. But anyway, so let's look at this blood sample. So this is a mass spec of the blood sample. What do you think? Is this a piece of evidence against this wife, this dutiful wife who's trying to collect insurance? What do you think? What am I looking for in the mass spectrum? If dioxin is in this patient's system.
The molecular weight.
Molecular weight, which was 324, right?
Three.
So I'm looking for that. So if I look at the mass spectrum, do I see that in pretty good abundance?
Yes.
I do. Right here. 325 is what? If this is the parent, what is 325?
M+1.
M+1 peak. Good. What is 289 in this spectrum?
The base peak.
It's the base peak. Right? So this is a pretty damning piece of evidence. If the blood sample, if you see this signature, at this particular signature in the blood sample, then this is going to be a pretty damning piece of evidence. What do you think all those other peaks are? What happens in a mass spec? When you take a molecule and you subject it to mass spec, what happens to
It breaks up.
Yeah, it fragments into pieces, right? So all these other pieces, if you look at try to keep it on the screen. If you look at all the other fragments, this is 289, which we said was the base peak. Right, and then 254, which you can't see, but it's right there. 219 is a fragment. And if you look at the fragments, what you're doing in this case is losing chlorine, right? So you're losing chlorines off that aromatic backbone first before you actually fragment the ring, right? The dioxygen ring, which holds those two pieces together. Right, and you have here at 184, you can see that peak. Right, 177, you can see that peak. 147, you can see that peak. And then 35 is just chlorine itself, right? Because chlorine has a atomic mass of 35. So that's just chlorine. All right. So you can safely say that this patient has dioxin in their system, and this might not be enough evidence to convict somebody of murder, but it definitely is a nail in the coffin, though. It's not like just a be all and end all, but a blood test that came back looking like this would most definitely play a role in getting this person convicted, because this is a very unique signature for this molecule, right? And the different fragmentation patterns. All right, let's go to let me go to this other handout. I'm gonna pull the mass spec examples out of this and put it with that PowerPoint when I post the notes. All right, so let's walk through this, and I'm actually gonna let y'all go, and the test will be posted probably about 10:30 or so. It is timed, but you have like 4 hours to take it, so you'll be good. I would choose a time where, because it's also, once you start it, you got to finish it. So when you start it, make sure you got time to finish it. It might not take you 4 hours, but you need to at least have intentions on finishing it in one sitting. All right. So let's look at the questions here, the little multiple choice questions. Which of the following is generated in a mass spectrometer prior to fragmentation? What happens to that molecule before it starts getting broken into pieces? What species do we make after we eject an electron initially?
The base peak.
The base peak is a fragment, and it says prior to fragmentation. So a base peak is actually a fragment.
The radical cation.
It's the radical cation. This is whatever that species may be, right? This is before it breaks up into pieces. First thing you have to do is eject an electron. So you bombard your sample with the electron beam, you force out an electron, and then you make the radical cation, which then goes on to fragment into multiple pieces. All right. What about number 2? What question does mass spec answer about a molecule?
B.
You said B, molecular weight?
Yeah.
Yep. So mass spec talks about molecular weight. NMR talks about the CH framework. UV-Vis is for pi systems. And then this is just a dummy answer. Not a dummy answer, but it's not an answer to anything. The other spectroscopic technique is infrared, which tells us about what functional groups are present. All right, let's look at number 3. Which of the following cleavage patterns do amines undergo? An amine, an example of an amine would be something like this. So what cleavage pattern would that undergo? We looked at 4 different cleavage patterns. We looked at branch point cleavage, allylic cleavage, dehydration, and what's the other one?
Thought it was alpha.
Hmm?
I mean, I know you have to look at the alpha carbons, but I just didn't know what it's called.
It's alpha cleavage. So for this molecule right here, this is where it will fragment. This is the alpha. That's alpha to the amine. So it's going to fragment here and here. So I would get out a CH2, CH3, and then I get this NH2. That's positive. That's my radical. And on the other side, I would get a CH3 radical, and then NH2, and I'll put the plus charge here. All right. So this next question asks, and I'll copy this page and pull it out. But this is what you actually would need to submit. It says draw the fragments from alpha cleavage, wrong pen, alpha cleavage of the following molecules and give their masses. What's the first thing we need to do in order to do that? Before we do any cleavage, what do we need to know?
What the alpha carbons are.
Okay, I agree with that. So here's one functional group, and then I got a carbonyl here. So that's alpha, and then that's alpha to the carbonyl, and that's alpha to the carbonyl. But what's the fundamental thing we need to know? Because if you're going to have to give the masses of the fragments, when you need to know the mass of the whole thing.
Okay.
Yeah. So that's for an example like this, that's the first thing I would do is to calculate the mass. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So that's 120. 10 carbons, the atomic mass is 12. And then 3, 6, 2, 4, 6, 8, 10. Hold up, let me count that again. 2, 4, 6, 8, 10, 12, 13. So 13 hydrogens plus 6 on the end. So that's 19 hydrogens total. That's 3, 6, and then 13. So yeah, so 19 hydrogens. Well, 20 hydrogens because the OH, sorry. And then we have 2 oxygens, that's 32. So the total 52 is 172. That way, you know, when you break your fragments up, they have to add up to 172, right? It's not going to be you can't lose mass or matter, right? So when you fragment this thing, the molecular weight of the fragments has to equal the molecular weight of the whole. So let's start working on, I'll just keep that part. Let's start working on.
I know.
Go ahead.
Sorry, sorry. I know the right one is the mean. The left one
You mean the
is
cleavage?
I just like naming the molecule. Like on the right, you have amine
Okay.
group.
So this would be a let me see, alpha beta. This is a gamma hydroxy ketone. But for the purposes of the discussion, we're just going to say that we're going to look at each functional group individually. So we'll look at the OH and the alpha cleavage for where the alcohol is, and we'll look at the ketone and the alpha cleavage for that. If that makes sense.
Okay. Yes.
Okay. All right. I was wondering, you had me confused there for a second, but but we're good now. All right. So I'm going to cleave here and then here separately, not at the same time. So if I let's call this A and B. So fragment A is going to look like this, not like that. That's a CH2. That's a plus charge there. And then I also have here, that's my ketone. Actually, I'm going to put the plus charge here and make this the radical. All right. Is that okay? Anybody disagree? Now, this is a complex molecule, so keep in mind, if I make this fragment right here, this big fragment, this thing can also fragment through alpha cleavage as well. So you're going to get a lot of fragments. But all I'm asking in this example is we're just looking at the fragmentation of the whole, right? But some certain fragments are able to fragment even further. Like something like this would definitely get broken up again. It would fragment again. Because not only would you have another alpha site here, that probably wouldn't happen, but the other two definitely. All right, so let's look at the other side. What do you think? If I cleave that B, what would I get?
Talking about
Would I get this?
now we're looking at the ketone. Are we now looking at ketone?
No, we're still looking at the alcohol, just the right side of it.
Okay. Yeah.
Would I get that?
Yes.
And then this. Is that right?
Yes. 2, 3.
Because I'm actually breaking this bond right here between those two atoms.
But it seems like on the left on the OH, it seems like there's an extra carbon. I always feel like
It's not.
was
Let's
this
count them. 1, 2, 3, 4. 1, 2, 3, 4. We're safe. right? So this is positive, and this is my radical. Plus charges, kind of grody looking. All right. Yes or no, maybe, somewhat. All right.
Okay.
You
Yes,
see it
I
now?
got it. Yes, I see it. Sorry.
It's okay. That's good that you asking that question though, because that means you at least are trying to visualize what the fragments look like. So that's okay. You're gonna have to do this one, and then you need to go back in and calculate the masses for these. Let me say this before I depart. Right, there is on this molecule right here, where that plus charge is. That is a cation, but that's also one hydrogen there. So when you're calculating the mass, don't forget that, because up here, there's a hydrogen right here, right? Just like there are 2 hydrogens on every vertex and 3 on every terminus, right? This is a CH3. So is this, right? So be mindful of that when you're calculating your masses, that, make sure you keep track of the hydrogens as well. All right, so you need to go in and calculate the masses, and you need to do the same thing for the second one over here. All right, any questions before we log out? And I'll probably grade. I didn't realize test 3 has so many workout problems on it, so I'll be grading that. I'll probably grade it tonight, so you can see your scores from that. I should have been graded it, but that's okay. I'll get it done.